Welcome back to ECE 441A, 541A. We finished exam 2. We have 2 more exams remaining, exam 3 and the final. And we also have a couple of labs that you still need to complete. Lab number 2 is due in a week. But before we get there, we will meet Wednesday, but Friday we will not meet in class. So I think people have already started practicing that protocol or process today, but maybe it's because we just finished exam number 2. Who knows? But we will meet Wednesday. We won't meet Friday. And I have posted the description of the project. If you're in ECE 541A, you should be able to find the project description for this class on D2L. Today what I want to do is pick up with Root Locus. That's what we're going to be immersed in for the next week or more. And you'll use that in lab number 3. And we'll start with just a word description, and then we will talk about the standard structure of the block diagram, or the standard structure of the expression that we will use to sketch the root locus. Then we will illustrate how to do it if we are confronted with something that doesn't begin in the standard form. How do we create the standard form from something that didn't originally look like the standard form? That will introduce us to really 2 conditions that govern all of the rules behind constructing these root locus diagrams. And that gives us a magnitude condition and a phase condition. And here are the rules. I don't expect you necessarily to write them down, but this is what you will be living and breathing for the next part of the semester. And I've tried to separate those rules into 6 sort of titles, or 6 labels. Where do we start and where do we end the root locus branches? Which of these real line segments are on the root locus, or what root locus segments are on the real axis? What's the asymptotic behavior as we crank up the gain k? And again, think of k like a knob that you're adjusting from 0 to infinity, and we want to see how do the closed loop poles migrate or move around the complex plane as we adjust that knob. We'll talk about breakaway and re-entry points of the root locus on the real line. Where does the root locus cross the imaginary axis, if it does? And then finally, the last rule concerns angles of arrival and departure. How do the root locus branches approach complex conjugate 0 pairs, or how do they depart from complex conjugate pole pairs? That will all, I hope, make a little bit more sense as we get into that. But here is something, if you are verbal, or if you like to read, here's your description, or a description of the root locus. It's a diagram in the complex S-plane that shows the location of the closed loop poles as the poles move around. As the poles move, as we adjust the gain k, these closed loop poles are going to move around the complex plane. And as we adjust k from 0 to infinity, we want to know what is the pattern that is associated with the closed loop poles, and that pattern or sketch is the root locus diagram. That's a description of the root locus diagram, and here are some examples of what I'm meaning, and the red lines are the root locus diagrams. So you can see that they are paths in the complex S-plane that depend on where the X's and the O's are. So now we will be, this is homecoming week, so I thought we would do a lot of X's and O's. That may not mean a thing to anyone, but sometimes you have offense and defense listed as X's and O's. Anyway, we use x's as poles and zeros as open circles, and depending on how those are positioned in the complex plane, that influences the red lines as they move through the complex plane. And we are going to learn how to sketch these red line diagrams, these root locus diagrams. Why do we know that the upper left root locus simply moves from the pole all the way to minus infinity and never gets off the real line? Why do we know in the upper right that the root locus actually leaves the two poles, but they leave and approach each other, and then once they merge, they immediately break off the real line. They break away from the real axis and depart at 90 degrees. Plus and minus 90 degrees, or 90 degrees and 270 degrees. It's however you want to measure, but we will be measuring angles relative to a positive real line segment in the counterclockwise direction. Then in the lower left, why is this sort of circular path down to the real line, and then one zips to a 0 and the other branch zips off to the minus infinity on the real line? And finally, we start in the lower right-hand plot with 3 poles, no zeros, and one pole, one branch of the root locus goes off to minus infinity. The other two actually go at plus and minus 60 degrees, we will learn, but they eventually become unstable if you crank up the gain high enough. So those are some pictures that by the third exam and the final you need to be able to draw. The red lines won't necessarily be on your paper, maybe not even the X's and the O's, and you'll have to put down the X's and O's and sketch the red lines. And what we want to do is hope to first learn how to sketch, but then maybe we will learn how to design. You will actually have a pole shaker and a zero shaker, not unlike salt and pepper, but you now have a pole shaker and a zero shaker, and you will be sprinkling poles and zeros on the complex plane. That's your controller design. Where do you put these poles and zeros based on your knowledge of how the root locus diagram is influenced by those pole and zero locations? Why? Because what we've already done is learn what regions of the complex S-plane we might want our closed-loop dominant poles to belong to or live in. All of this is building on itself. Here's the standard root locus form equation that we will refer to throughout our discussion. And it will be associated with a ratio of 2 polynomials. We'll have a numerator polynomial n and a denominator polynomial d, and we'll speak to the zeros in this equation being the roots of n of s, and the poles of this expression being the roots of d of s. But n and s and d and s, depending on how we actually start, may not be quite what we started with in terms of zeros and poles in g's and h's and g sub c's, etc. It will depend on how we've now created or converted our characteristic equation into this standard root locus form. And that's what we want to talk about now, is how do we convert a given characteristic equation into the standard root locus form. And when I say standard root locus form, now I hope you bought a stack of 50 or 100 index cards, because you're now sleeping on another one before exam number 3. You're now putting that equation on your index card, and now you can put that under your pillow. Sleep is very important. Index cards maybe not so much, but hopefully it makes the point. Here's our example. Suppose we now are given the following characteristic equation. and it involves a k, and maybe we now have the ability to adjust that k from 0 to infinity, and we want to know what values of s will satisfy that characteristic equation. For whatever reason, this equation now confronts you. Maybe, well, what this would be the denominator expression in a closed loop transfer function. It's now in this form, and we want to put it into the form indicated by star. Our objective is we want to convert that polynomial in S into a 1 plus k times a polynomial over another polynomial. That's the idea. It's just algebra. That's all we're going to be doing to manipulate delta of S into star. So we're making, apparently before this class, somebody was in here with glue and glitter. We're now going to be converting deltas into stars. So we're kind of getting into the creative spirit. Maybe it doesn't involve as much glue and glitter, but use your imagination. So now we have deltas and stars. We want to derive, how do we get star from delta? And here's the answer. I'm going to just give us the answer. Since it's a Monday morning, maybe you want to kind of know where we headed. Here's where we will end up, but I want to now show you the steps, and it's not a very elaborate process, but how do we get from that delta of S equal to 0 into an expression that I've stated is in the back of the book. Here's our answer. 1 plus k. Now we have a factor s plus 3 divided by some combination or polynomial in s, and it's a quadratic in the denominator. So how did we get from delta to this? That's our goal. We want to convert from delta to star. And here's the process. So now we can sort of slow down and work through the steps. The first thing that we want to do in our delta expression is to actually isolate the terms in that expression that involve the adjustable parameter k. Our delta expression started with s plus k times s plus 3 plus s plus 1 equaling 0. That's how we started, or that's what we began with. That's our characteristic equation. We want to now isolate the terms involving k. And the way that we can do that in this case is simply distribute s plus k across that factor s plus 3. Or we now just multiply that first term out. You can keep the s plus 3 together, but now we say plus k s plus 3 plus s plus 1. Now granted, we're trying to get to a star, but this is not rocket science. All right? All we did is do a little bit of multiplication. And that shouldn't be too earth-shattering. The second step is now to simply divide through by all of the terms that don't multiply k. Here, I'll just write that down. Divide through by the terms in that delta of s equation not multiplying k. And the terms that are not multiplying k, I hope you can see, are those. So now we want to divide both sides by that combination of s times s plus 3 plus s plus 1. Both sides are going to be divided by that. Or we have s times s plus 3 plus ks plus 3 plus s plus 1 equaling 0. But now what we want to do is actually divide both sides through by s plus 3 plus s plus 1. And we can do that. We can multiply an equation by 1. We've now multiplied by, or divided both sides by s times s plus 3 plus s plus 1. And now all we have to do is just a little manipulation. We simply realize or see what that piece gives rise to. We now have the same piece in the numerator as we have in the denominator, which now allows us to convert all of that that's highlighted in yellow or circled in yellow by a 1. We just have s times s plus 3 plus the quantity s plus 1 divided by that same term. That gives us 1. We end up with plus k times an s plus 3 over s plus 3 plus s plus 1. And I hope you can now appreciate that this is our n of s that we said we wanted to find. And the denominator gives us our d of s. And if we wanted to, we could look at that d of s. D of s is now s squared plus 3s plus s, or 4s plus 1. Where are the roots of that d of s located? Are they located in any particular part of the complex s-plane? Can you make that immediate conclusion or draw that conclusion from what you see for d of s without any calculators? You don't have to bring your calculator today. You maybe should have over the exam, but not too much of a impact, hopefully. But where are those? Where are the roots? What values of s cause that d of s to vanish? Where are they? If I said put your x's in the first quadrant of the s-plane, in the second quadrant, in the third quadrant, in the fourth quadrant, in the right half plane, in the left half plane, where would you locate those roots? Hopefully, you say the left half plane, right? Because those two coefficients are present and positive. It's a quadratic. We know immediately if those two coefficients are present and positive, the roots are in the left half plane. And in fact, if you did factor this, you would see that its factors are 0.268 and s plus 3.732. So a little bit more than a quarter and a little bit less than 4. But you now have two real poles at minus 0.27 and minus 3.7 associated with d of s. And so now we could put all of that, we could rewrite our equation as k, it depends on my mood whether I will put k up in the numerator or by itself on the left, but here is now s plus 0.268, s plus 3.732. There is our standard root locus structure, and we will call this factor the open loop zero factor. This is just the terminology that we will use when we are sketching the root locus. And this collection of factors will be the open loop pole factors. Just establishing terminology. So now let's look at another example where this might actually arise. So here's an example. With a block diagram, how are the closed loop poles in this block diagram that I'm going to sketch in just a minute, how are the closed loop poles affected by adjusting K from K equals 0 to K approaching infinity? And that's giving us the root locus. But here is the diagram that I want to use. Suppose we have one transfer function that has two pole factors in it. We have a 1 over S block. And just to make it a little bit different than what we're used to seeing, how about I put the K in here? So for whatever reason, this is now our configuration that we're playing with or using, and this we want to now sketch the root locus associated with this diagram, and in particular, where do the closed loop poles belong in the complex S-plane as K is adjusted from 0 up to infinity in this diagram. What's our closed loop transfer function? That's what we want to find, because we want to work with the characteristic equation, which is the equation that is associated with the denominator of our closed loop transfer function. Why did I say that's equal to 0? I have no idea, because I was thinking about the denominator and setting it to 0. This is now what I'm calling the closed loop transfer function between R, the input, and Y, the output. And maybe you guys are already so skilled in this that you can, by inspection, just write this down. Maybe you can see that that's 1 over S, S plus 1, S plus 2, plus KS plus 1. Did you see that? No? Oh, come on. But that's what we should get. How do we get that? Or what's one way? Let's use Mason's gain. So if we're using Mason's gain to find that, what's our strategy? Paths and loops, right? What's one path from R to Y? Hopefully you see that as just right there, right? The obvious. There's our path from R to Y. So now P1, if we wanted to find that closed loop transfer function using Mason's gain, is 1 over S, S plus 1, S plus 2. Do we have any other paths from R to Y in this configuration? Sometimes you have to be a little bit careful trying to find those, but in this case we do not have any more paths from R to Y. Do we have any loops? We have a big loop right there, and we have a smaller loop right there. So let's now write down those, yellow being 1 and blue being 2. So loop 1 is the big loop. That's minus 1 over s, s plus 1, s plus 2. And loop 2 is minus k over s plus 1, s plus 2. We okay with those paths and loops? Do we have any other loops? No. So now we can start creating our transfer function. What's the determinant, which is not our delta of s? So do you see how I overuse or overload these symbols? We don't have enough symbols to go around. But here I'm using delta as our determinant. That's this 1 minus L1 plus L2 plus L1, L2 minus, if we needed what? If we had non-touching loops, but those loops touch, so we don't have the product of L1 and L2. And what's delta 1? What's the cofactor associated with path 1? If I eliminate path 1, do I disconnect any loops? I break them all, don't I? So my cofactor delta 1 is just 1. And now I have my transfer function. T of s is now P1 delta 1 over delta, or that's now 1 over s, s plus 1, s plus 2, times delta 1 over 1 plus the term coming from our first loop and the other term coming from our second loop. And now we can put all of that, the numerator and denominator, over a common denominator of s times s plus 1, s plus 2. So I can essentially put an s in the numerator and denominator there. And now T of s will become 1 over s, s plus 1, s plus 2, plus 1 plus ks. We okay with that? And that should have been what was in the back of the book when we started. Our characteristic equation is now determined by setting the denominator polynomial equal to 0. So here is that overloaded notation. Maybe I should use, didn't I say sometimes I would use Q? Let me use a Q here, although I promised we would go from deltas to stars, didn't I? Oh boy. Oh well, we'll have to change. Sorry, I promised you deltas. We're going to go from Q's to stars. Q is now s, s plus 1, s plus 2, plus ks plus 1. And we want to now put that in the standard root locus form. Which is 1 plus k n of s over d of s equaling 0. And that's pretty easy to do, isn't it? We just identify all the terms that don't involve k, divide by those, and we end up with the expression we need. Or our expression now for the standard root locus form from q of s ends up being 1 plus k times s over s plus 1, s plus 2 plus 1. If this is now our expression, what have we agreed terminology-wise will be our open loop zeros in this standard form? What is the numerator polynomial? What's n of s? That's just s. And so what are our open loop zeros? The values of s that cause that polynomial to vanish. We actually have a 0 at 0. What about our open loop poles? Those are found by setting d of s equal to 0. d of s is now, if we start multiplying that out, we have s squared plus 3s plus 2 plus 1, or that's now s cubed plus 3s squared plus 2s plus 1. This is now our d of s. If we set that equal to 0, what values of s cause that to vanish? Or you could now sketch that curve and see, does it cross 0 for real values of s? And in fact, this one does not. This is a cubic, but if you sketched this, you would see that it does something like that. And so it only crosses 0 if this is now s and this is d of s. It crosses 0 only at one point, which is actually minus 2.3, and then it doesn't cross again. So if we have a cubic that has one real root, where are the other roots? They're complex conjugate, aren't they? We have real coefficients, so if we did the roots of that, we would find that in fact we have roots at minus 2.3 and minus 0.34 plus and minus j 0.56. And those are what we are calling our open loop poles. Again, this is homecoming week, so we need to be comfortable with x's and o's. Where are the x's in our complex s-plane? Our x's are going to be where these open loop poles are. We have one that's real at minus 2.3 and two x's that are complex conjugates. Let me now try to sketch those. So we have one pole at, well, let me do the complex ones first. Minus 0.3 plus and minus j 0.5. Let's say that's where those are. And now if that's minus a third, then I need to go quite a bit further to get that. Where's our 0? It was at 0, so now we have a 0 right there. And what we want to do is draw these red lines. Do you see any pattern here that looks like what we just have with x's and o's? The only pattern we have here with a 0 is in the lower left, we do have two complex poles, but we have a third real pole, so we don't have anything similar to what I gave you as examples from before. So we now have to figure out, how do we sketch the root locus for this collection of poles and zeros? And in fact, let me just confuse you even more with two possible pictures. And it will be one or the other, but based on not having any other way of calculating right now, we could guess or speculate that there's two possible patterns for the root locus diagram. And I better switch to red. So one such diagram might be that this pole decides to just walk all the way in to the 0. That's one branch of our root locus. So in terms of root locus, just getting us thinking, how many poles do we have in this diagram? That's not a difficult question. There we have 3. So we're going to have 3 branches of the root locus. We should have 3 branches, and sometimes those branches are on the same line segment, and so you think, well, I just have one branch, but there's actually 2 branches on one line segment. So it can get confusing, but we now have 3 branches of the root locus. In this example, I'm saying the one branch goes from minus 2.3 into the origin, and the others are doing that. And I'm hoping that it's clear that these are now approaching some asymptote line that goes up and down vertically, or it's at plus and minus 90 degrees. So those root locus branches will actually, one will shoot up to infinity at j omega, and the other one will go down as k gets increased from 0 to infinity down to minus infinity in the imaginary direction. That's one possible pattern. I promised you a second, so I better deliver. What's another possible pattern? If we had the same, and like I said, we're only going to really have one of these pictures. But another possibility might be that they all like to sort of play together a little bit more than this guy indicated. So now these complex poles, they may want to come down and meet up with this particular. Let me do that over again. Let me say that they come down here, and they're leaving the pole. One trips over here, one goes over here and meets up with that one, and then these two break away and go there. Oh my goodness. Which pattern is it? Well, we will learn using the rules of root locus construction why it's one of these and not the other. One of these patterns just doesn't belong. For some reason that came back with Sesame Street. I don't know where that came from. But anyway, this is a second pattern. And we now need to study the root locus so that we can figure out which pattern it actually is. How many branches do we have in this diagram? How many root locus branches do we have? How many poles did we start with? 3. We can't grow or eliminate any branches. We have to have 3 branches. And where those branches are, it's really, here's one. Let's say this guy goes here and there. There's one branch. Another branch, this one goes here, and then he decides, oh, you know what, I want to go up. And then we have another, what color do I want? So now this one says, oh, I'm going here. Oh, he went up, I have to go down. So they're the 3 branches of the root locus. Even though it looks like, oh my goodness, look how many arrowheads he has or how many arrows he has, but there's only 3 branches in that root locus diagram. There's 3 poles, 3 branches. Similarly up here, it's pretty clear that we have 3 branches there. This one makes that question a little bit more interesting. Where are the branches? And it doesn't matter whether the 2 that meet go up and one goes down, or the 2 that meet, one goes right and one goes left. There's nothing political here at all. They're just, one goes right and one goes left, one goes up, one goes down. Okay? We need to figure out how that happens. So let's move on. The root locus is really concerned within paths, or what I've now been calling branches, in the complex S-plane that actually show or demonstrate how the closed loop poles change as this adjustable parameter k is varied from k equal to 0 to k going to infinity. What that means is, in this diagram, at k equal to 0, do you know where the closed loop poles are? At k equal to 0, where are the closed loop poles? They're right on the x's. Then as I adjust k, maybe I crank up k to 1/2. Well, then these 2 might get here. They have to be in conjugate pairs, and this one is now there. I have 3 triangle locations for a given value of k. What if I crank up k to 2? I'm just being hypothetical here, but now maybe they say, oh, at 2, I'm going to be at that cloud location, I'm going to be at that cloud location, and this one's going to be right there. What if I crank k up to 5? Then these 2 clouds that are complex conjugates have now merged and separated. What shape can I use now? Let me make a diamond. So there is a diamond, there is a diamond, and this one is right there. That's maybe k equal whatever I just said, 5. Let's say k equals 6. Now these 2 diamonds that are going towards each other have met and separated, and this one is getting close to that 0. So as I adjust k, these crazy shapes are moving symmetrically around this root locus diagram. And if I wanted closed loop poles at the clouds, I would pick k at that value, whatever I said that was, k equal 2. If I wanted my closed loop poles to be at the triangles, I would say, oh, k is 1/2. That's where I want my poles. Or if I wanted it to be where the stars are, then I might crank up k to 8, or whatever I said it was, 6 maybe. Is that clear? As I'm adjusting this knob k from 0 to infinity, the closed loop poles are moving according to those red lines on the complex S-plane. They can't, if somebody said, oh, you know what, I picked a k of 6, and here was a closed loop pole, and here was another one, and here was another one, I would say, well, you just lost all the points on that problem, because there's no way a closed loop pole can be anywhere other than where the root locus is. That root locus is telling us where the closed loop poles are based on your system's configuration, interconnection structure. That's why we're sketching these root locus, so that we can figure out where are our closed loop poles. Questions on that? Then we're ready to get back to our basic block diagram structure that we will use during this root locus discussion. Suppose I have a controller and a plant or a system, and maybe I also isolate the gain in my system outside that set of poles and zeros in G sub C. Here's the controller. Here's the plant. There's our output Y. Here's our reference input R, and maybe we feed this back through some more dynamics H. And what we do here at the summing junction, typically most of the time it's going to be a negative, but we might also have positive feedback. So here is the negative feedback, and if we had a positive sign, that would be the positive feedback. What's our closed loop transfer function based on either of those two possible signs on our feedback? In grading the exam, well, here, before I get to grading, maybe what I should have done is said, let me call that a bar. I don't like to introduce bars, as I've said before, in a collegiate environment, but there's a G bar. Here is maybe just G in general is the product of G sub C and G bar. If that's the case, what is our closed loop transfer function? I was talking about grading the exam, and somebody said cheer 2, and then they wrote down the formula for the closed loop transfer function. I was encouraged. Okay, it doesn't take much, but when I hear cheers, I get encouraged, or when I read cheers. So what's the cheer that we can use to find the closed loop transfer function? And cheer 2 was based on what? Negative output feedback. And that was G over 1 plus GH. And now we have G sub C, G bar, K, H, but I hope now we've grown up, we haven't spent too much time with G bar, to be able to figure out what's G and H and where K goes. But in this case, I hope that it's clear that the closed loop transfer function, T of S, would be g, which in this case is k g sub c g bar over 1 plus k g sub c g bar h, and that plus is with negative feedback. And if we had positive feedback, we would have had a minus sign in that denominator. And we will pick up at that point next time. But this is now, if somebody gives you positive feedback, you just have to modify the denominator as a 1 minus that sum of terms.